this is the beginning of the class, and it's a lecture on graph theory, which is quite an important topic in math as well as in competitive programming. And we're waiting for people to join, and we're going to start soon. Okay, so graph theory. Typically, we represent a graph. Typically, we represent a graph by writing G of V comma E, where V is the set of vertices and E is the set of edges. And graphs can be of two broad kinds: undirected, where both vertices corresponding to an edge are sort of equivalent, and directed, where one vertex kind of points to the other. So you can go from, say, this vertex to that one, but not the other way around. And next, in graph theory, two graphs are considered equal if all of their vertices and all their edges are sort of in the correct place. It doesn't matter how you draw it. You could draw it however you like, but the connections should be the same. For example, in this one, it looks like the first graph, but the connections are different. For example, 1 to 5. Okay, so we generally denote vertices by small letters such as U, V, W, and edges by small letters E, F, G, or edges can also be represented by the corresponding two vertices which they connect. And also vertex and node are used interchangeably in graph theory. They mean the same thing. Some other important terms and definition regarding graphs are these. So first one is adjacency. Two vertices U and V are said to be adjacent if there is an edge connecting them. And then a path is a sequence of vertices that are unique. So V0, V1 to Vk are all different for it to be a path, such that Vi and Vi minus 1 are adjacent. So basically what this means is that you can sort of go from V0 to Vk if you think of vertices as cities and edges as, say, roads. You can go from V0 to Vk. That is a path. And a cycle is also a path with V0 is equal to Vk. So you can start at one vertex and come back to it without repeating any vertices in between. And a connected component is a subset of the graph such that for all vertices belonging to this connected component, there is a path from one to the other, but there is no path from this to any vertex outside. Then we have trees. Trees are a special kind of graph, and this is what a typical tree would maybe look like if you draw it. It can have flowers or maybe mangoes, but because computer scientists are boring, they only have leaves, and also they draw it upside down because it's believed that they've never seen a real tree. Anyway, by definition, a tree is an acyclic connected graph. That's the formal definition. So that means it doesn't contain a cycle, and you can go from every vertex to every other vertex. Here are three graphs, A, B, and C, and I'd like you to tell me which one is not a tree. And here I am asking my audience, and Ananya answered B, which is correct because it should be connected, right? But in B, you can't go from, say, 1 to 3, and therefore it's not connected, so it's not a tree. It has two connected components, as we would say. What about the other two, A and C? Are both of them graphs? I mean trees? Of course they're graphs. And then, yeah, Deepika and Ananya answered correctly that A is not a graph. Sorry, not a tree, because it contains a cycle, and trees should not contain cycles. So yeah, C is the only tree out of these three. Now, an interesting question is, how many edges does a tree have if it has n vertices? And this was given as a homework problem, so yeah, people should try to prove it themselves. Ananya answered that there are n-1 edges, which was the correct answer. But yeah, you should try to prove it yourself. It's quite fun. Next, we would move on to a special kind of tree called a rooted tree, which looks like a typical tree that you might see in a garden, but inverted. Yeah. So, we generally, if we are given a tree, we can arbitrarily pick a root and fix it, and then we can make directed edges from the root to its neighbors, and then from those neighbors to the next neighbors, and so on. And this is what we call a rooted tree, and they are pretty useful data structures for implementing various, functionalities such as sets and ordered maps. And some definitions related to rooted trees are depth and height. So a depth of a node is the number of edges on the path from the root to that vertex. So for example, if you pick this vertex, it has depth 1 because there's only one edge from the root to here. The root, of course, has depth 0 because there are no edges. And this other vertex, it has depth 3 because there are 3 edges on the path from the root to this. And note that this is well defined because a tree cannot have cycles. So you can't have like 2 different length paths from the root to the vertex. A height is kind of similar. Okay, so over there, Ananya asked me a question, which was whether rooted trees have to be directed or if we arbitrarily draw the edges or how it works. So typically, if you are given any graph, you can just take a random vertex and call it the root and then make your edges directed. And why this is useful is because then there's this notion of parent and children and, least common ancestor. And as I said, to implement data structures like maps and sets, you need this rooted tree structure. But yeah, there was a third definition of a parent and a child, as I said. So for any edge, the vertex towards which the head points, like the arrow, that is called the child. And the vertex where the tail points, that is called the parent. So this is the parent, and this is the child of that parent. You'll learn in the following lectures why these definitions are important. Now, binary trees, again, data structures such as maps and heaps, and heap is basically a priority queue, and like sets. So in sets, what you do is you maintain this invariant in a binary tree that if a vertex is to the left of another vertex, like it's the left child, then it's less than the parent. If it's the right child, it's greater than the parent. And that's why it helps to, have exactly two children, because left side will be less and right side will be more. And when you do this, when you make like a complete tree, which means that all of the nodes except the leaf nodes have exactly two children, what happens is the number of vertices is 2 to the power n minus 1, but the height is only n. So kind of in log n operations, you can reach any vertex that you want, and that is useful for retrieving information in maps and sets. So it's just a special kind of tree. Okay, so far we've been talking about trees in a kind of abstract way, in a mathematical way, where, we're drawing dots and lines for vertices and edges. But a computer can't see dots and lines, right? That's what we see. So in order to explain to a computer that this vertex is different from this vertex, you would need some sort of a method, some sort of an algorithm or a data structure to store them. The most common one that we use in competitive programming is an adjacency list. There are also two more ways, an adjacency matrix and a third way, which is like a tree class, where you make you make a class called tree, and then you have a subclass node within it, and you link all of the children to the parent. But that's just for a tree. For an adjacency list, first we number each vertex to differentiate them from each other, and next we store the neighbors of each vertex in a list and combine it to make a bigger list, and this bigger list is called the adjacency list. For example, here the list corresponding to 1 would store 2, and the list corresponding to 2 would store 1 and 3, and so on. So here are lists of all the neighbors of each element. You can check that this is correct, hopefully. 1 has neighbor 2, 2 has neighbors 1 and 3, 3 has 2, 4, 9, 6, and so on. And then you store it in a bigger list. Now this is useful because the neighbors of 1 are stored in the first position, neighbors of 2 are stored in the second position. So if you have this in, say, a vector data structure in C++, you can easily access everything. Next, there is a data structure called an adjacency matrix. This is how we just write matrices mathematically, A(n × n) or Aij. It means that, it's an n × n matrix, and the ijth element is equal to 1 if there is an edge from Vi to Vj, and it is 0 if there is no edge from Vi to Vj. Some interesting facts are that for undirected graphs, A is symmetric, because you would have an edge like this, for example, and so if you can go from I to J, you can come back from J to I as well. So Aij would be equal to Aji. But in directed graphs, that might not be the case. They don't need to be symmetric. Now another interesting fact is that if you raise an adjacency matrix to some power, basically multiplied by itself multiple times, then the ijth element of a to the power k contains the number of walks from vi to vj with lengths exactly k. A walk is similar to a path, but the restriction that all of the vertices have to be unique is removed. So walk counts a superset of paths, basically, where you can repeat vertices in between. And luckily, I do have a proof for this, and I'm going to prove it now. Okay, so we're going to prove this by induction. The base case is k is equal to 1. This is true by definition, right? Because the number of walks of length 1 are simply corresponding to the edges. So, for example, the number of walks from vi to vj is 1 if there is an edge from vi to vj and 0 otherwise. So, this holds by definition. Next, we move on to the inductive step. So first we assume that the statement is true for k is equal to m. Then if we let p is equal to a to the power m, then pij stores the number of paths from vi to vj with length exactly m. This is our inductive hypothesis. Now we take q is equal to a to the power m plus 1, which is the same as p times a. Now, by the laws of matrix multiplication, we get this equation: qij is equal to summation from r equals 1 to n pir into arj. And we can break it down into two different summations, one where arj is 1 and one where arj is 0. So arj is 1 when there is a walk of length 1 from r to j, and it is 0 otherwise. So we can break the sum into these two parts and just get rid of the second part, because a is 0, so multiplying anything with 0 gives you 0. And we're only left with this part. Okay, so we can think of R as sort of the breaking point where we would get all of the walks from vi to vj of length m plus 1. If we get all of the walks from vi to vr, which is where vr is any neighbor of vj, and because you can only get to vj from one of its neighbors in one step, so you want to get to its neighbors in m steps. And this is exactly what PIR counts, because by the inductive hypothesis, PIR is the number of paths from VI to VR of length exactly m. And R and VR correspond to the vertices that are neighbors of Vj. So, yeah, this counts exactly the quantity that we want. You sum the number of walks from Vi to VR over all neighbors of Vj. And this would give you the number of walks from Vi to Vj that have length exactly equal to m plus 1. And we're done. That was the proof. I hope you understood it. An interesting fact is that if you change this definition a little bit, so instead of only having ns from Vi to Vj, you also make it 1 if like I is equal to j. Then a to the power k would store a different quantity. As you can see, I was struggling to write I is equal to j a little bit, so bear with me. Almost done. Nope. Okay, there we go. Success. Alright. So if we change this statement a little bit, then a to the power k, the ijth element of a to the power k would store the number of walks from I to j of length at most k instead of exactly k, which is quite fun in my opinion. But yeah, next we move on to search algorithms. Search algorithms are basically algorithms which traverse a graph. That means they visit every vertex of the graph at least once. The two most common search algorithms that we use are depth first search, which is called DFS in short, and breadth first search, which is called BFS in short. So the idea behind DFS is to explore each path as far as possible. So you pick one path basically, so you start from one vertex and you visit some neighbor, and then again you visit some neighbor that you haven't already visited, and you do this until you have no more unvisited neighbors, and then you start going back. So you kind of backtrack and go back to the parent, which is the node that you came from, and then try to see if there are any other paths left to explore. And when you're done exploring that, you mark it explored, and then you go back, and so on. This is the code for implementing it, but it is slightly wrong, which I realized later. So mark v explored is supposed to go before the for loop, because otherwise you can go into an infinite recursion, and that's not good. That will lead to TLE when you do this on CF. So how this works is that you start at any node, say V, and then you mark V explored. This is so that if the graph contains cycles, then this is just to prevent you from coming back to it from another path and calling DFS on it again, because if your graph contains cycles, you could get stuck in a loop and keep going back again and again, and that would not be good. As I said, it would lead to TLE. So for each unexplored neighbor of V, you call DFS on that neighbor, and yeah, this is how the recursive function works. And basically the guarantee, so suppose you call DFS on vertex 1 in this case. So you go to 1, you mark it explored, and then you go to 2, you mark 2 explored, then you go to the neighbors of 2, 5 and 3, you pick one of them, say 5 in this case, and you mark that explored. You can pick arbitrarily, I just chose 5 because why not. And then you go to the neighbors of 5, arbitrarily pick one, then you go to 7 because that's the only one that you can go because 5 has already been marked. So you go to 7, mark that, then you go to 6. This is the moment when I realized that it was a bit wrong. Yeah, so you go to 7, and the only neighbor that has not been explored is 6. So you visit 6 and then you mark it, and then again the only unexplored neighbor is 4. So you go to 4, you mark 4, and then you start going back. So now whenever you go back, you can kind of start listing your vertices to maybe tell someone which all vertices you visited. So like basically once you add a number to this list, it means that you have visited that and you have explored all possible paths from that, and there is nowhere else to go after this vertex. So yeah, you backtrack to 6, then to 7, and you came to 7 from 8, remember? Yeah. So you mark 8, then you go to 5. And note how we were supposed to run a for loop on the neighborhood of 5. But 7 is already explored, so we don't do that. So the function that just exits when it's supposed to visit 7. And then we go back to 2 and visit its neighbor 3, mark it, then go back to 2 and back to 1 again. And we are done exploring the entire graph. I hope you understood. This is a very important and very interesting algorithm. You could try and prove its correctness as well. Next is BFS. Now the idea behind BFS is to explore a graph layer by layer. So you first visit one vertex, then you visit each of its neighbors, and then instead of picking one neighbor and going down a path along it as far as possible, you don't do that. You go to all of the neighbors one by one and then visit just one layer further into each, and then keep doing that so that you don't completely exhaust a path, but you explore all paths at once. This is generally implemented using a queue data structure, because in a queue you push elements at the end and take them out from the other side, right? So whatever goes first comes out first. So you start with any vertex, add that vertex to queue, and while the queue is not empty, you add all of the unexplored neighbors of the top vertex and then dequeue the top vertex. By top, I mean the first one that was sent into the queue the earliest. Okay, so we start with this. We initialize the queue with just 1, and then because the queue is not empty, we dequeue 1, and then we go to 1's neighbors, which is just 2 here. And then we enqueue 2 into the queue. Yeah, and then because the queue is again not empty, while the queue is not empty, you dequeue the first element from the queue, and so we dequeue 2 and go to its neighbors. Then one by one, we enqueue the neighbors. Yeah, so we add. So we enqueue 2 now, because 2 is an unexplored neighbor of 1. And note that in this queue, I'm going to mark the removed elements yellow, I'm going to highlight them in yellow so that you know that they're not in the queue anymore. I'm just doing this for more clarity, and I don't have to, you can think of those elements as having been removed already. So yeah, we add 2, and now there was a while loop and the queue is not empty. So you dequeue 2, look at its neighbors, see which are unvisited, and then you enqueue the unvisited neighbors, 5 and then 3. Awesome. Next, the queue is still not empty, so we dequeue 5, which is the first element and add its neighbors, the unexplored neighbors. So 8 and 7. And again, not empty. So DQ3. And from 3 you have nowhere to go because all of its neighbors have already been explored. So you do nothing in this iteration of the loop. But the queue is still not empty. So you next DQ8. Then you look at the neighbors of 8, but all of them have already been explored. So you do nothing, but the queue is still not empty. So you DQ7. And 7 does have unvisited neighbors. One of them is 6. The only one is 6. So you add 6 to the queue and you mark it explored. Next you DQ6, NQ its neighbors, unvisited neighbors, and mark them explored. And yeah, we're done. Almost. You DQ4 and yep, done. Because 4 has no other unexplored neighbors. So that was BFS. I hope you understood. But some things to keep in mind while you use these algorithms is that if your graph is not connected, then both of these algorithms will only visit like the connected component of the graph containing the vertex that you start with. However, you can make a pretty simple modification to fix this. So whenever there exists an unexplored vertex of V, vertex V of the graph tree, you just call DFS on V. And in practice, you would implement this using, say, a visited array, which is an array of length equal to the number of vertices, and you initialize it to all false. So you haven't visited any vertex initially. And then as you mark things explored, like in while explaining the examples, I was saying that you have to mark it explored. While writing code, that would mean that you would set the corresponding element in the visited array to true. And you would run a for loop that says for like each vertex from 1 to n, if if you visited this, then skip, and if you've not visited it, then run DFS. So yeah, each time you don't have to check whether there's an unvisited vertex or not. You just run a simple for loop, and that will do things efficiently. Another nice thing about this is that since each run of the DFS only captures one connected component, you can use this to count how many connected components there are. So inside this for loop over all vertices, whenever you run DFS, you increment your counter by 1. And that would give you the number of connected components in total in your graph. Alright, that is pretty cool. So like if you want to go from one connected component to another, you would have to, say, add another edge between them. And another thing to note is the time complexity. Both algorithms run in O of V plus E time, where like mod V is the number of vertices and mod E is the number of edges. And the space complexity is mod V, because as you saw in both algorithms, whenever I added an element to the queue or to the list of visited elements, I can only add as many as the number of vertices that there are. I can't add more than that ever. So yeah, that's how much memory it takes. And I could prove this rigorously. If you want me to, I can send it on the group. You can ask me. But yeah, you should try doing it yourselves instead, because then you would understand better. So, but the idea is that in BFS, you visit each vertex only once, and then from that vertex, you visit each edge corresponding to that vertex, and each edge has only 2 vertices corresponding to it. So since you visit each vertex only once, you can visit each edge only twice, because you can either visit from one vertex corresponding to the edge or the other vertex. There's no other way you could ever traverse, you could ever think of going to any edge. So that's why the time complexity is of V plus E in BFS. And for DFS also you can use a similar argument. You never revisit a visited vertex, so you visit each vertex only once. Actually you visit each vertex twice, because once while going there and once while coming back. This means that you can visit each edge at most twice as well, because you traverse along an edge at most twice. If your edge is U, V, then if you visit U first, then you go from U to V, and then back from V to U, and you never visit that vertex again. So yeah, the complexity is of V plus E. Next, I was also supposed to cover cycle detection. So I'm just going to tell you how it works. It's really simple. So whenever you do BFS or DFS, both of them work for cycle detection, and you notice that you visited a vertex and it has an already explored neighbor which is not its parent, then you know that it must have a cycle, and this vertex must be part of that cycle, because whenever you see that there are 2 ways to go from one vertex to another, there are 2 paths to go from one vertex to another, then there must be a cycle. Because if your path is, say, V0, V1, V2, V3 up to Vk, this is one path, and your other path is V0 to say U1, U2 till UK minus 1 and then Vk, then you get a cycle if you go from like V0, V1, V2 up to Vk, and then UK minus 1, UK minus 2 all the way till U2, U1 and V0. So yeah, that's how you detect cycles in a graph. Pretty simple. Alright, now we end the lecture if no one has any questions. Thank you so much for attending, and thank you to the 3 people who unmuted and talked to me in the class. I will forever be grateful. Alright, bye-bye.